Спасибо всем за подключение. Дарья, вам на русском удобно или на английском? Как легче?
Как хотите.
Хорошо. Ну, давайте тогда официально скажем, что welcome everybody to our next session. This is our 7th day of winter online school within the SpaceCom project. And today we have the lecturer on the theme communication cancellations, and also a little bit about CubeSat technology continues from the Daria Stepanov from Exolaunch company. Daria, if you're ready, floor is yours. Пожалуйста.
Yeah, thank you very much. I'm just gonna start the screen sharing. You see the screen, right?
Yes.
Okay, great. All right, good morning, everybody. I'm really happy to see you once again. This is going to be our second session, second day today. And I'm going to split it into big groups. The first would be, we'll continue the discussion about CubeSat engineering. And today we're going to go deeper in subsystems, and we'll see how these subsystems interact with each other, how do we go through design process, and what are the differences between different approaches in this design. And the second part of the lecture will be dedicated to communication constellations. There we'll see what's the current state of constellations dedicated for communications. We'll go through several big constellations which have started back in 90s, and we'll review two of them, and another two we'll see just the current constellations. We'll see what's the difference between them, and we'll discuss the challenges they're gonna face in the near future. And we'll start with the CubeSat engineering part. As for organizational questions, I would propose the same concept. We'll have around 45-50 minutes talk, and then 10 minutes break, and that's gonna be repeated 3 times. And if you have any questions, please don't hesitate to interrupt me during the presentation. It would be great to have open discussion. All right. The first part, CubeSat's technology is, we're gonna split it in 7 big topics. The first one is CubeSat structures, then mechanisms. The next would be electrical power system, and what's the components of the system. After that, we'll go to onboard computers. We'll continue with communication systems. The next system to review would be attitude, determination, and control, and we'll finish this part of the lecture with space debris topic. And we'll start with CubeSat structures. Basically, there are 3 major design drivers for the CubeSat structure development. First one is stability, and stability is evaluated as an ability to resist bending moments, some buckling forces, and other deformation forces. Basically, the structure shall be stable in terms of loads which are applied for the satellite during manufacturing, handling, testing, and obviously the launch itself. The stiffness is defined as ability to resist dynamic inclinations and or vibrations, and that's the major design driver for the launch of the satellite. And the strength, the last design driver, is defined as ability to resist static forces without the rupture. Basically, yes, so these 3 design drivers are defining the materials which are used for structures. They're defining the structural approach. How do we, with the shape of the outer of the satellite and inner parts of the satellite as well. There are 3 basic big blocks in the structural hierarchy. The structure for CubeSats is divided like by the primary. This is the cube you can see below. So that's the main rails and the brackets which are connecting these rails. So this structure carries like the major loads during the launch, and basically it has to carry like the launch loads. In other words, like as we remember, based on the CubeSat design specification, these rails are the only interface between the satellite and between the deployer. So all the loads are affecting the satellite like from this sides, from all the sides, and they're influencing the rails. So basically these rails and the structure which is connecting these rails shall be as stiff as possible. The second part of the structure is the secondary, basically. This includes thrusters, panels, booms, antennas, and the components which are not really carrying the loads. That might be also like some brackets inside the satellite, which are stiffened enough. And yeah, on the picture you can see some like hinges for solar cells or antenna holders. And the last one is territory. These are components housing, brackets, fasteners, and other additional mechanical components. That's basically here what can be mentioned, that in our project we are mostly using like commercially available components for housing and for like fastening for brackets. However, we pay a lot of attention in the materials which are used for that components, and conduct some testing prior to using them in our systems. Some of the components we're using can be also done, like they do not need to be made of metal. We're also using plastic ones, but once we're talking about plastic, it's important to remember outgassing parameters of the plastic components. A few words about the primary structure. So that's pretty much the core of the spacecraft, and it's the thing which is interfacing the deployers. It has to carry all the load which the satellite will experience during the launch, and it carries tensile and compressive stress. Here in the picture you can see some like resonant modes of the CubeSat structure. So basically during the launch, satellite can be affected like by this force and by this force, and star structure shall carry all these loads and not let the components get detached or get broken under this stress or bending moments. There are a couple of like major requirements for primary structure. So it shall provide load path between spacecraft and the launch vehicle. And as you can see, there are two bending forces. So the structure needs to accommodate these forces in a like optimal way. It's a mechanical interface to launch vehicle. Yeah, like I've just briefly mentioned that already. It shall also provide access to components and assemblies during ground operations. And for example, one big challenge which CubeSat developers are facing, so these panels are normally covered with solar panels, which is like the last components, mostly the last component to be attached to the satellite. And it's pretty hard to connect like the last connectors to this panel. So the structure shall be designed in a way that all components shall be accessed in a easy and fast way, and all the cables can be attached also in a like easy and fast and optimal way. Structure carries the dead weight of the spacecraft. So besides the launch vehicle, it shall also carry the weight inside the satellite. It shall secure positional stability for antennas and other instruments after launch and under changing temperature conditions. So temperature expanding and shall be also taken into account while designing the structure. Antennas placement and instruments placement is in particular important because of the radiation patterns and the pointing of the instruments and the mission objects, which can influence the mission objectives afterwards. So the structure shall provide the stability of display, so the antenna shall not be moved away, or the camera telescope also shall not be misaligned after launch. Stiffness and uncritical natural frequencies shall be also handled by the structure. There are several ways to assemble the satellite, several methodologies which CubeSat providers are using. The first one is the deck mounting. Basically, all the components are stacked inside the satellite, and then the sides of the satellite are closed. Another one is panel mounting. In this case, components, internal components are placed on the sides of the satellite, and the basic structure is not carrying any components, and as during the satellite assembly, all the panels are closed together with components. Here you can see the two examples of deck mounting and panel mounting. Pretty much what I have said in the deck mounting, components placed inside, and these two covers are the last pieces to get assembled. In the panel mounting, a lot of components are placed outside, and we can see a little bit of a mess here with the harnessing and with isolation. Yeah, but basically that's the concept and the idea. Another two ways which were mostly, like, they found a lot of applications in small satellites and CubeSat in particular. These are stack configuration and slot configuration. Stack configuration is something similar to like computers or to like PCs, using some standard connectors as PC104 or some slot edge connectors. Several PCBs are attached for the backplane PCB, and this is later assembled from the sides, stacking components like on top. The big disadvantage of this approach is in the if we need to take like during the testing or during the assembly, for example, one of the components gets broken, or like, there's an urgency to substitute the component. It's required to disassemble the whole stack and then start the assembly process from the beginning. Slot configuration, yeah, is something similar. It's just differs from stack. There can be several slots, and slots are a little bit easier to disassemble. And like you can see the connectors like on this side, and slots are attached to this edge connectors. Yeah, like, so regarding CubeSats, here you can see the evaluation of each of the packaging options. Deck mounting is not really suitable for CubeSats because yeah, there's no deck, particular deck in the CubeSat. Stack configuration is the one which is the most commonly used in the satellites, and once all of them are connected, so that's either the ribbon cable backplane or standard connector, which is PC104 style, is used. However, integration and replacements, as I said, requires a lot of additional efforts, as is disintegration. Panel mounting is possible in the small satellites. However, due to size limitations, it's pretty hard to handle. So the panels, they have to be somehow connected, so that already makes it more hard. That makes it harder to develop the harnessing inside the satellite, which brings to the complex wiring. The integration procedure becomes more difficult and most likely irreversible, because once the panels are mounted and everything is connected, it's quite hard to break in some connections and break in some attachment points. Might make the procedure irreversible. Slot configuration is like a really interesting alternative to stack configuration. It uses the spec plane. And the replacement can be done in an easy and fast way. However, we didn't see like many CubeSats with this packaging option. Mostly, I think due to vibrations, the stack connector can get a little bit damaged. So the big question here, how to ensure the good connection between the board and the connector without advancing too much the mounting of that, and not like making this stack configuration. We will review some of the examples for the structural concept, and the first one is this Mia Huakai CubeSat from the University of Hawaii. They use the solid structure. You can see there are not so many cutouts, just looks a big piece of metal. However, like some of the advantages are the easy mathematical modeling. So basically, this kind of structure most likely will carry all the necessary loads. It was pretty easy in manufacturing, and integration was easy. However, the satellite itself like became quite heavy, and there is no possibility to accommodate components outside. So basically, once designing solar panels, like all the components of the solar panel shall be on the outside, like all the diodes and connectors, which is not always really easy to make. The next one is the Cal Poly CP1 CubeSat architecture. So this is it consists of two modules connected like with this diagonal shape bodies. It's pretty lightweight. It can accommodate components on the outside and pretty flexible with the inside accommodation. The printed circuit boards of the size of from 100 to 80 millimeters square can be accommodated inside. However, this structure is pretty hard to model and to analyze in terms of stiffness and strength. The integration procedure might be pretty complex, and obviously the manufacturing cost of this shape is higher than comparing to the structure we've seen before. On this one, we see the DTU SAT-1 made by Denmark Technical University. The structure is pretty lightweight. It's a good size. That's standard PC104, which is 98 by 96 millimeters square. However, this structure limits the payload designer with some larger component placement in the satellite. This structure requires higher manufacturing efforts and some costly aluminum alloy because of the, again, stiffness and strength with this shape, if not provided by the structural construction, but shall be done by the material selection. And the complex integration procedures is still here. Another interesting approach was developed by TI-SAT. This also looks like just a big piece of metal. This one has a good thermal conducting and radiation shielding. So basically, if like all the sides of the satellite are made of steel or made of aluminum, like provides a good safety for the radiation. It's like really custom made to meet specific mission requirements. So there are cutouts in the structure we can see, which are specifically adjusted for one type of payload. In case there are any design flaws or there is another iteration of the payload and this access windows can change in time, there's a high risk of the structure not being suitable anymore. So the integration procedure might be quite demanding, and the design, overall design might be quite complex. Yeah, this is how it looks. Yeah, there are a couple of mounting points, access windows. However, as I said, like all these parts might be also hard to manufacture. Interesting concept. It was made by ISIS. This is the CubeSat structure. I think most of the CubeSat companies got inspiration from. Like this one is really easy to buy. There is an online shop for CubeSat components, which is similar to the normal online shop. It's available in many different form factors from 1U until 6U and already 12U. It's quite cost-effective solutions. However, customers have to comply with PC104 standard, so the mounting holes for the PCBs in the structure already fixed, and in case the satellite designer wants to use another PCB sizes, there shall be like another bracket or something which will attach the new design for the structure. There are not so many options for deployables, so the structure tries to accommodate as maximum possible volume in the deployer, thus limiting the space on the outside of the satellite. So, and the share panel mounts are fixed, so yeah, there are not also many options how to adjust the panel mounts. The last, I think, CubeSat structure is made by CubeSat Kit. We see that there is an isogrid pattern which helps a lot to enhance the stability and resistance of the structure. Like side panels might be solid to allow any customer configurations. Basically, this pattern might be changed to some like special payloads. This structure is also available in like different form factors. So basically the structure was a starting point for some commercially available components. Including these shapes in the structure, there is already a limited capability to accommodate custom parts. So in case there is a payload which has some specific aperture looking outside of the satellite, it shall comply with these cutouts. Size accuracy restricted by use of bent metal sheets. So as these sides are sheets made of sheet metal, there shall be other structural components like these main brackets, top and bottom, which has to carry all the loads. And again, limited options for deployables. Oh yeah, as you can see, the CubeSat structure that we are providing has been inspired by this isogrid pattern. It consists of small number of parts and pretty easy in integration, lightweight and high stiffness. We're making it from aluminum alloy, which helps us to achieve the high temperature stability. From the disadvantages point of view, it's also mostly carry the PC104. There are some brackets available for other types of other form factors of the internal components, and low integration density is also one of the disadvantages of our structure. A quick summary on the structures. It has to be made out of aluminum for good thermal properties and the good interface matching in between the satellite and launch adapter. CubeSat configuration is actually determined by the primary structure. So that primary structure sides, apertures, openings are on one side are defined by the payloads and by the systems which are in the satellite. However, they also dictate the composition of the satellite and their placement. Many CubeSat projects develop structures on their own. That's true because the structure is not the most complicated component of the satellite. So like many manufacturers are pretty free to design it by themselves. From some interesting points, approximately 20% of total mass of the satellite is due to the structural elements. So they tend to be over-dimensioned to limitations in manufacturing small wireframe structures. So composite materials, there are some structures made of composites, and I think there were several experiments launching the composite structures. However, it's not as publicly utilized as I think it might be in a couple of years. For CubeSat structures, launch loads like sinusoidal, random vibration, acoustic, and shocks are pretty much harmless. So that's due to the design approach and material selection. In case one day you'll decide to build your own CubeSat structure, there are a couple of things to remember. In case you want to do it by yourself, it's pretty simple and easy in the design. Tolerances are quite relaxed compared to like some other systems. If you're making it by yourself, you can easily change and adapt it to commercial solutions or get inspired by them. The material selection will later influence the coating options. Yes, regarding the coating, I think we discussed it last time. So the rails shall be anodized to prevent the welding in between the deployer and the CubeSat. And the structure shall be also optimized for thermal conduction. Some of the important notices are also that the structure shall not be designed as like the first part of the satellite project. It's always good to have this back and forth in the design where the electrical or the payload components are integrated in the structure in CAD, and 3D model is being adjusted. So in this way, it's much easier to prevent some like big mistakes of components not fitting in the structure of the satellite. Integration procedures shall be considered during the design. So basically, knowing how to assemble the satellite early enough in the satellite project is also a crucial part. Accounting for long lead times might be helpful while iterating several structural designs. And like as we know, sometimes components can be delayed, and in terms of structure, I think based on my experience, that was the component which was delayed the most of the time. So it's also necessary to have like additional timings when it's possible to delay a little bit the finalization of the structure. All right, basically, so there are these steps in structural design, so design or redesign, manufacturing, coating, finalizing, assembly, and integration. This is the flow of the structural life in the CubeSat. And with this, we're going to the second topic, which are mechanisms. Do you have any questions so far regarding the CubeSat structures? Or everything is fine?
Okay, thank you. Is there any questions?
Okay, if there are no questions, I'll continue with mechanisms.
Yeah.
There are a couple of types of mechanisms in the CubeSats, and the first one, all the CubeSats shall have, based on the CubeSat design specification, are deployment switches. These are really like small sub-miniature micro switches, which are attached to some spring mechanism. Like basically you can see it over here. This is the structural components, the structural side. This is the rail, like in the cross section of the rail. This is this micro miniature switch, spring, and some, it can be screw, it can be just some cylinder made of metal. Yes, so like once the satellite is in the deployer, this switch is pressed and the satellite battery is detached from this from the rest of the components. When the satellite is deployed on the orbit, this switch gets unpressed, and basically the battery then is connected to the main of the system. So this component every CubeSat shall have and shall like accommodate either in the rail side or like it shall be somewhere on the rail, because there shall be connection in between this mechanism and the deployer side. And here, like you can see the internal parts of the switches. The next one is the solar panel hinges or solar panel deployment mechanisms. You can see several times folded solar panels. Basically, this is like pretty easy mechanism. Hinges are also supported by springs, and the panel is folded several times. And then the mechanism, which is really similar to antenna release mechanism, which I'm going to talk about in a few seconds, is used. And once on orbit, this mechanism is activated and the solar panel, due to the spring forces, is deployed. Antenna release mechanisms for CubeSat, there are several types. Most often it's electrically powered heating wire made of some nichrome, and it's pretty much the antenna is attached to some either like plastic or any type of the material part with this nylon string. Once on orbit, this the wire is heated and the nylon filament is melted. On this picture, you can see the example of the BSAT antenna release mechanism. Instead of heating wire, like this nichrome heating wire, it's possible also to use like resistor or any other component which can be warmed up pretty quickly and does not outgas so much. So that was the like pretty easy, pretty fast, really easy to reinstall mechanism approach. There are more interesting like antenna mechanisms. For example, this one is accommodating up to 4 antennas of different lengths. All these antennas are stopped inside this like really small compartment. But inside of this compartment, absolutely the same approach is utilized. So there's also the melting wire and the heater, which are activated at some point, and then due to the spring forces in this part, the kind of the legs of the antenna release mechanisms are opened. This mechanism is a little bit more difficult to handle and to reinstall. However, it's quite small in the shape and can accommodate up to 4 antennas. All right, that was briefly about the mechanisms. And from here, we will continue with power control and distribution system.
About the parts, there was a question about the solar panel.
Okay.
Is it same, I mean, the normal one, or it is special solar panels?
You mean solar?
Yep.
These are standard CubeSat solar panels. Basically, the solar panels normally use space-grade solar cells. There are 2 big companies which are providing the cells, which is one is Azure Space, another Solar. Yeah, I mean, most of the CubeSats are using this kind of solar.
So they are not the same with what we are installing in our houses.
Oh no, these yes, they're really different. The ones we're installing in our houses are much cheaper. They use this different technology. They're mostly like one-time junction, and these one are triple junction gallium arsenide cells. They have up to 30% efficiency, and the ones we're using on the ground are most of the time like 15 maximum or 16 percent efficiency. Like I'm going to talk about that in the electrical power system, but solar panels are one of the most expensive component of the CubeSat, and it's better not to save budget when we're talking about electrical power system and solar panels, especially, and communication system. I think there were CubeSats which were using like more relaxed solar cells and solar panels. However, like with double less efficiency, you have double less power in the end, and it's either experiment takes more time or there's not enough power for the mission and for the experiment. So the solar cells shall be like really good quality and really space grade.
Can you give us the names of the solar panels? So types or?
So the solar cells, for example, we are purchasing solar cells from the company called Azure Space.
How? Row space?
Azure space.
Azure space.
Yes.
Okay. Thank you.
Yeah, however, like in Azure space, they're selling just this solar cells components, but then like all the solar panel has a little bit more complicated design. So for example, the protection from the solar cell failure, the maximum power point tracking, the thermal control, and so on. So like at our company, for example, we're taking like the cells and we are providing the design of the solar panels of different like shapes and so on. And yeah, they're pretty much every CubeSat company is doing that. All right. The next power control and distribution system. But there are four main tasks the system is doing. First one is the conversion, storage, and the distribution of electrical energy. And here we remember such components as solar panels, batteries, and control modules for distribution and processing. Acquisition of system health parameters. As soon as the power is distributed between systems, it's also required to get a feedback about do they consume like enough current, or is there some anomaly which makes them consume more power than was specified. Operations of switches and systems monitoring are the third and the fourth one. So general requirements for the power control system are listed here. EPS shall provide a continuous supply with electrical power. It shall control and distribute electrical power between payloads and the main bus. It shall support requirements of peak and average power. For example, once the communication modules go into transmit state, or there is some system which is turning on, draws a lot of power, like current at that moment, power system shall take this into account and either smoothen or prevent from turning on the system. It shall provide telecommand capability for systems control. Basically, that means that we shall be able to send a telecommand to turn on or to turn off the system. It shall provide telemetry capability for system status. That includes like power consumption. Is the voltage level correct? Is there any fault in the system switch? Activation and deactivation of assemblies, protection of spacecraft against failures of the power system. And here we shall also consider redundancy in some of the main components, avoidance of single point errors and redundancy strategies. Basically, that's what I just said. The EPS shall also consider orbit type, like in terms of height and inclination that will influence like the solar cycles. Mission line planned, this mostly influence the batteries charging and discharging cycles. Solar array pointing area, and so on. So these were like system requirements. If we're talking about mission specific requirements, there shall be type of the power supply bus. There can be several types. Bus voltages, these are normally like 3.3 volts, 5 volts, unregulated, and 12 and going higher already. Energy and power demand in different satellite operation modes. That's we're gonna see a little bit closer in the next slide, but that depends on the number of active components and their duty cycles. Type and amount of system health statuses, measurements, values, and this includes current voltages. It can include also temperatures. Yeah, these are most commonly used. And we'll not go into detail of like every of these requirements. And based on this example, power control distribution unit from the satellite, we'll see how the design process is and how do we go through all these requirements to get the proper system working in the end. So basically, there are three main blocks in the EPS, how we just discussed. The first one is conversion. So the power comes from solar panels normally in CubeSats. The storage, which is the battery, and generation and processing and distribution units. In order to increase the reliability of the system, the additional redundancy is added to the system. Here we can see there are 2 batteries. Solar panels are supplying the chargers with the 9 volts voltage, like the power level of 9 volts, and the battery are supplied from the solar panels with the solar energy through these charge regulators. We need DC to DC converter here because I think the output of the solar panels in this case was like 4.2 volts. Thus, we need to boost the voltage level a little bit up because it has to be higher than the maximum battery voltage. Charge regulators are this kind of autonomous switching units, which based on the voltage and current level from the solar panels and the charger, like the state of the charge of the battery, which is most of the time it's just like the voltage level of the battery decides either it's time to charge the battery or it's the battery is completely charged. Then from the charger regulator, the power line goes to 2 converters, in our case 5 volts and 3.3 volts, and each of these power buses is then supplied to the switches. As I mentioned, here are the solar panels and solar cells. We are purchasing them from Azure Space Company. The triple junction gallium arsenide solar cells with 30% efficiencies. We're using in this satellite the configuration of 5 panels with 2 cells on each, and one panel was accommodating 8 cells, but that was like more experimental thing. In this kind of small CubeSat, the available power was around 2 watts, and that was like pretty much enough for all the experiments we wanted to conduct. Here you can see also how the solar cell itself is looking. Right, so that's the datasheet screenshot, which shows what are the parameters of the solar cell. Average open circuit voltage is 2.5 at the beginning of life, and average short circuit current is 16.9 milliamp per centimeter square. So if we calculate the area of the cell, we'll get the average short circuit current. There are also some temperature gradient characteristics, which are also important to include in the power budget analysis, for example, because the efficiency of the solar panel, like not the efficiency, but the curve which connects voltage and current of the solar panel is influenced by the temperature. And as we see, the solar cells are black, so they might get pretty hot in the sun. This will also influence the power on the output of the solar cell. Regarding the batteries, here you can see the battery type we were using before in our satellite projects. This is the Varta micro battery with nominal voltage of 7.4 volts. It's based on lithium polymer technology. And the capacity of one block like that is more than 1 amp hours. The critical thing here is the battery can be charged when the temperature of the battery is more than 0 degrees. In order to prevent the battery failure and charging in the cold, we're also adding some additional heaters and temperature monitoring in the battery pack. Maximum storage energy of 2 battery packs, for example, which are used in the satellite, this BSat was 19 watt hours. Basically, 2 battery packs were used. Power control unit is the unit which is responsible for processing and distribution of the power. It is based on one microcontroller, which is controlling all the switches. It gets the information about switcher states and power consumption of all the modules through analog to digital converters. In that case, it was like 16 channels on each converter. There is a circuit with integrated watchdog, which is helping from the latch ups during on-orbit operation. The basic principle of this system is following. The main switch is controlling the power coming to this microcontroller, and the watchdog has a specific period of time where it shall receive the signal from the microcontroller. If it does not, it resets the main switch, basically enable signal, and main switch does not feed power to the microcontroller anymore. In this case, in terms of in case of microcontroller failure to send the signal to watchdog, obviously something has happened and the power of the microcontroller is reset. In this way, it's possible to save the microcontroller in case of some particle event is happening. The microcontroller is also connected to two CAN buses. There is a redundant CAN bus introduced in the satellite, and for that there are two transceivers installed. And this one, you can see the first prototype of this control module. It had 24 switchable components for turning on and off external systems. Via CAN bus, it was possible to set the default onboard computer parameters, choose internal external software images, set ADC thresholds, activate or monitor these thresholds, and set the PCU clock. So the request for these values was done from the onboard computer via this redundant CAN bus. And this was already the final design of the system. I think it looks much more prettier. In several design iterations, we achieved that this system can be suitable for 1, 2U, and 3U CubeSat designs. So here, the DCPS can control up to 16 power buses, features power distribution unit, yes, with this 16 buses. It is really failure tolerant, and it monitors every channel. You can set up the channel parameters via the software. Power switches can be configured to different power buses and different voltage levels. Main bus is independent from the power control unit and cannot be switched off in case of failure. So that means if the main microcontroller of electrical power system is failing, then the power channels which are selected will be still operating, and it will still be possible to get signals from the satellite. On this slide, you can see the updated EPS block diagram coming from this prototype to this system. What has changed? We still have solar panels controllers. The power here goes to bypass load switch, and through this load switch, it feeds the power control unit, the unit with microcontroller, watchdog, and yes, CAN transceiver. We also added the I2C isolator to expand the amount of interfaces available. So the second power line goes to the load switch. That's the main switch which activates or deactivates all the satellite subsystems, but the power control unit. Here there's this boost converter for 9 volts and the battery charger and the battery connector. After that, the power either from solar panels or the battery is coming to the system load switch and to the power processing module. Here there are several connectors for 3.3, 5. There are also several references, voltages, levels, or unregulated voltage can be put through the system, through power distribution system to the switches assemblies. Besides these 8 switch subsystems switches, there are also dedicated sun sensor switch, antenna release switches, and magnet docker switches, which are going then to the system connectors. And here I think we can make a short break. Like 50 minutes of the lecture have passed. Would that be fine?
I think yes, but here one more question. If you saw, what type of battery recommended to use in CubeSats?
So lithium polymer.
Okay. So it is also some kind of specially designed, or?
These ones are not specially designed, they're commercial off the shelf. So we do not put much effort in or much resources in purchasing some space grade batteries. However, we provide the comfortable conditions for the batteries in terms of temperature, in terms of battery monitoring, so in terms of charging. Yeah, so like some batteries have a specific charging profile, and we try to put more effort in designing proper system to work with these batteries.
Okay.
It is explosion free. You never had any problems with explosions. Yes. Yeah.
Okay.
So yeah, there are.
Thank you.
My question.
Yes, Dr. Ege?
Excuse me. My name is Bakhtiar Palwanov. I am a physics and research in semiconductor structure. We are using in preparing solar cells. I have one question. Можно на русском вопрос?
Да.
Хотел узнать, какой параметр КПД солнечный
Сейчас немножко прерывается связь, я плохо слышу.
А у нас интернет очень неустойчивый работает.
Какой параметр КПД? И дальше я не расслышала.
Да, вопрос, пожалуйста, еще раз.
Время использования этого солнечной панели. Вот.
Да, но в принципе у всех солнечных панелей есть такой beginning of life и end of life. End of life зависит от конца миссии. Наши миссии, например, они рассчитаны на 2 года, и просто в дизайне power budget и расчета энергетических характеристик мы учитываем вот эти 2 года. В дата-шите, который предлагают производители солнечных ячеек, в принципе, указаны end of life параметры, и они обычно там, не больше 10% за 2 года. Так что, надеюсь, это ответ на ваш вопрос. Или я просто не расслышала что-то.
Ну, если у вас будет вопросы, просто напишите.
Хорошо.
Спасибо.
Да, хорошо, тогда можно 8 минут перерыв, и тогда в 10 минут соберемся еще.
Хорошо, 10 минут.
Угу.
Спасибо.